Good evening, Fancy Meet Computers. How is everybody doing this fine Thursday evening? I hope everybody is, at home, snugly in their study space. It's doing that echo thing again. Eat the mic, they say. Eat the mic. Is this better? Let me hear. Test, 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 test. 1, 2, 3, 1, 2, 3. Yeah, that's considerable improvement. Alright. Maybe the sound waves are like reflecting off of the wall and then into the microphone or something like that. Yeah. Alright. Alright. Eat the mic. Hello. Hello. Welcome. This is WKRB Talk City Radio. This evening we have our guest, Dr. Helen Amazing Imagine, Chief Psychologist of the city's Psychology Department. Helen, how are you this evening? Need to put a headphone warning. Yeah, I should just have a permanent one at the top, eh? Alright. So. Oh, by the way, microphone, embedded system. Ha. ASMR. Yeah, excellent. So, anyway. Alan couldn't make it this evening. Good. Excellent. Got 40 people watching. Hopefully we can boost that up to like 50. Oh, announcements. I should talk about the announcements, actually. There have been a couple of announcements in kind of short succession. Today has been a day of lots of information coming out. So, there we go. So, yes. So let's start with the lab kits. So I got some official documentation from the department about like how much the lab kits are going to be and that sort of thing. So we should go over the details. So, this is all you need to know about lab kits. First of all, the deposit on the lab kits has been settled at $125 and will be fully refundable at the end of term. So you'll get the full deposit back, assuming that you return the kit in good condition. So getting your deposit back will be contingent on your kit being returned in good condition. If you fry your board, you won't get the deposit back. Or the full deposit back, anyway. Like, if your stepper motor is fine, but you fried your board, you'll get a partial refund. You'll get basically a refund, or a rebate, or, you'll get the money back for the parts you didn't ruin. Lab kits will be distributed next week during your tutorial sessions. If you miss this session for some reason, the kits will be available the following week. Hopefully you don't miss 2 in a row, but, at any rate, the kits will be in the lab and you sign them out from the TAs, right? So you will sign out your lab kit. There will be a sign-out sheet. You will, put your name in and you will acknowledge that you are being charged for this. And what will then happen is the TA takes that sign-out sheet, gives a copy of it to the department, and the department is going to automatically charge your student account for the amount of the deposit. So please do not bring any money to your lab session. This is not a cash transaction. We're not taking credit cards or debit cards. Do not bring money. It's going to be done through your student account. At the end of the term, your deposit will also be refunded in the same manner. We will not be handing out cash, so it'll go in through your student account. It'll come out through your student account. Everything will be taking place electronically. Of course, that means that if you don't transfer those funds into your student account, the university will charge you interest on that amount while the semester is going on. So you'll probably want to electronically transfer that anyway, and I don't know if there's any mechanism. There's probably a mechanism to get the money out of your student account, but anyway, it's between you and student accounts at that point. I don't really have anything more to do about it. At the end of the semester, your lab kit must be returned during your final lab session, or failing that, to the lab coordinator, Robert Lee, in ITB 242 by April 12th. April 12th is the cutoff for it. If you don't do it by April 12th, you won't get your deposit back, or you will not get all of your deposit back, or something. I'm not sure, but I was told make sure everything's in by April 12th. And yes, lab kits are still mandatory, even though lab sessions will be in person. Trust me, around Lab 3, you'll be really happy to be able to work on your systems outside of class time. Any more questions, post them to Piazza. So I have some questions here. Has the number of MSAFs changed throughout the semester? I haven't heard anything about that. I know that they're going from a 3-day applicability window to a 5-day applicability window, but I haven't heard anything about them giving you more than one MSAF. I don't know. I haven't heard anything about that so far, so I'm going to assume that the current wisdom is no. But they've also been talking. I don't know if you guys got sent the latest briefing, but they're talking a lot in that that release that they just did about how, as a professor, I'm supposed to be a little more flexible with deadlines because of the whole COVID thing. So probably it'll be basically what they were doing last year, which is you get one MSAF, but if you want a second one, you apply for it, and they'll probably give it to you, I guess, but you have to do a little more paperwork. Can you choose to keep the kit still? We would appreciate it if all kits were returned at the end of the semester. This isn't a purchase, this is a deposit on something we expect back. It is the expectation of the department that we get all the boards back. Other than the board, are there any relatively expensive parts? I think the most expensive thing in there, other than the board, would be the stepper motor. Computer fans are not particularly expensive. Everything else is like chip size or, LED size. I suppose the wiring kit and the breadboard are the other big ticket items in there. There goes my plan of paying in pennies. Ha! Take that, penny payers. Is it the full deposit? Yeah, if you return the lab kit in good condition, then you'll receive the full amount of the deposit back again. So you get the full $125 back. Is it one MSAF per term or one MSAF per semester? A term and a semester are the same unit of time, so yes. Can you get someone else to sign it out for you? No, you gotta sign for it. It's a legal contract, actually, so you're the one who has to sign for it. I'm peaking my mic a bit. Oh, yeah, okay, I'll turn the gain down. Yep. I'm speaking a little closer to it than I usually do. How's this? Is this better? Yeah. Sorry about that. How's that? Is this a little bit better? Test, test, test. 1, 2, 3. Testing! Hopefully. Good. Sorry, do we have to pay the $125 before we get the refund, or do we just wait till we get the refund? So this is, as I understand it, this is the process. You sign out the kit. When the admin office receives the list of people who actually signed out your student account will be charged the $125, pardon me. When you return your lab kit, there will be another sign-in page, or it'll be sign out, then sign back in. And the TA has to sign off that all of the parts are good, right? When you get on that list, and that list goes to the department office, Once that paperwork is processed, $125 will be credited to your student account. So there's no cash in this transaction. Will we be returning the entire kit, or can we keep the consumables? The instruction that I've received is entire kit, please. It still peaks. I feel your gain is too high. Not that you're too close. Yeah, it's probably... Yeah, okay. Gain down. Test, test, test. How's that? Is this a little bit better? Let me listen to it for myself. Testing, 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 testing. 1, 2, 3. Yeah. So, good. Excellent, excellent. Thank you. So, I see that labs... Okay, so... Shut up, me. So, brief comment about Lab Zero quiz. So the Lab Zero quiz is the lab safety quiz. I've made it available. It's basically, you're going to be given time in lab to fill out the lab safety quiz, like next week during your tutorial. I know that like the distinction between labs and tutorials is somewhat fuzzy. I'll probably just refer to them as lab sessions in general, accidentally a number of times. But yeah, the lab safety quiz, you don't have to do it now. Don't worry, unless like you're going to be given in-class time to do it, so I wouldn't worry about it too much. And besides, there's going to be a lab safety briefing, so don't worry about it. It's there, though. If you really want to fill it out, then feel free. But, you know, you don't have to. Pay the deposit. You can be charged a late fee. Happened to people in a different course first semester. Yes. Yeah, so while having a credit on your student account is not detrimental, especially because that amount can be used against your tuition next year, having a debt on your student account will accrue interest. So I would highly recommend using electronic transfer to put the $125 into your student account. If you're the kind of person who doesn't keep anything on your student account, I think the meal card draws from the same pool, but, you know, again, that would be a question for student accounts. When does the interest begin on the student account? I believe you've got until the middle of next month, but again, these are questions for the Office of Student Accounts. Really not my... It's kind of above my pay grade, you know? So yeah, so that's everything you need to know about lab kits. So let's talk about the COVID update, then. So, the Office of the Vice Provost has asked all instructors to make clear their policies regarding absence due to self-isolation and illness. It is anticipated, as the semester goes on, that a number of you will be taken out of in-person learning by either self-isolation due to adjacency to a positive tested person, or getting a positive test yourself, or actually, you know, being sick with it. That's, you know, those are the sort of three categories that are in my brain, at least. So, first, and we already touched on this, it's important to note that the university has stated that it's expanding the MSAF applicability period from 5 days to 3. So normally when you use an MSAF, you can apply it to any assessment from any class for a 3-day period. With this guy, you can apply it to any assessment from any class within a 5-day period. The number of MSAFs, as I understand it, they have not talked about altering the number of MSAFs, but my understanding is that they've been a lot more free with them this year. The second MSAFs, I received a number of second MSAFs last semester from various students, so there's a separate process for that. It has to go through the faculty office, but there's a procedure in place for it. So this is going to affect us perhaps a bit more than the other classes I teach. Like, I also teach 1MD3, which is like intro Python programming, and that thing is completely online. So there's really like, there's no I was just about to say there's no benefit to coming in person, but that's not true. There's like everything's already set up online anyway, so there's no, penalty essentially for being online with it. This class, however, the lab sessions are in person as well as the tutorial sessions, so we're going to need a little bit. We're going to need more of a robust policy. So, first of all, if you have a cold or a positive test or any other criteria that would prevent you from getting a green checkmark on MacCheck, you are to stay home, obviously. Number 2, I have instructed the TAs to keep an MS Teams meeting running during the lab sessions that they're supervising. So basically the plan is, so long as you are able to work, like if you're isolating but you're still able to work because you're not sick, you are to attend the lab session virtually. Basically, we'll have a virtual component. There will be people doing it virtually, people doing it in person. The TAs are going to have to manage that, so please be kind to them because it's not easy. I know this from experience. So that's going to require a webcam because they have to be able to see that your embedded system is running, so you need to be able to give them a video feed. Probably the webcam built into your laptop, if you have one, will work adequately for that purpose. But yeah, you'll need some way to be able to stream video. If you are self-isolating but can still work, you are expected to participate in the lab at the time the lab is occurring. If you are too sick to work, then file an MSAF, right? And the MSAF policy that's already been laid out, has been laid out in the course outline, that will be the applicable policy. Are there any questions about any of that so far? I know I took a long time going over this stuff, but it's kind of important. Just to remind everyone, tutorials and labs will be in person. I managed to get our course designated as, in-person learning is preferable, and trust me, it is much better for your learning for you to be in the labs, right? If you're in the lab, you can just call a TA over and say, I don't know what this electronic circuit is doing, and the TA can be like, oh, well, it's obviously this, that, and the other. You can just, rewire it or whatever. The TA can help you, right? They can help you with the physical elements of the lab. When it comes to doing the lab remotely, that becomes a lot more difficult for the TA because, you basically have to present a video of what's going on with your setup, and it might not be obvious, from a webcam that you're using the wrong resistor or something like that, because the video feed tends to be poor, right? So there is definitely an advantage to coming into lab. You are expected to come into the lab sessions if you're not self-isolating. Basically, if you are eligible for the green check mark on MacCheck, you are expected to be in lab physically. All right? Good. So, if there are no further questions with respect to any of that, I think we can proceed on with the lecture material for today. Good. 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 Wonderful. So, When we left off, we just had a little bit to wrap up in this introductory topic. So this last bit of it is essentially going over the major topics in the course. So I won't dwell on it too long, but it's still useful and important information. So we've talked about what an embedded system is. And if we want to design one, it would be good to know what are the required key areas of knowledge and skills that are required to do so. So, what do we need to know? First, we need to know what logic gates are and how combinational or sequential circuits implement different functionalities. That's a prerequisite. So, is it 2E04, the electronics course that's done by the EngPhys department, I think? Should have a lab component where you were wiring together all kinds of circuits. That course, whatever digital electronics course you took before you got here, that's going to be required knowledge here, just so you know. So, we also need to know what programmable devices are and how they can be programmed. Is it 2E04? Yep. I got it. I took that course way back in the day. My TA was a horrible, just a trash individual, just a garbage human. You could tell that the world had told him in not so many words that it would prefer him to not be on it, and he had taken that to heart. That's the type of TA that I had for that course. Anyway, a million years ago. I can't remember names. This is oh my god, 15 years ago I took that course. On the order of 15 years ago. So, what are microprocessors, microcontrollers, microcomputers, digital signal processors, and peripheral devices? We need to know what all of these things are. How are these components interconnected to create a complete system? The best I can remember about my Calc 4 prof was that he was Russian. Yeah, I'm older than I look, right? Yeah, I was class of 2010 for my undergrad. Again, I don't really remember any of my professors' names, except the ones in the CAS department. So we need to know how these components are interconnected to create a complete system. We need to know how a processor works and how a program runs on it. We need to know what an interrupt service routine is and how it services interrupts. And we also need to know why interrupts are important. Cole's Notes version. You remember from 2MP3 that I was talking about signals at the end of the class? Interrupt service routines are essentially signals. So, interrupts are essentially signals. Interrupt service routines are essentially like signal handling functions. That's, See, 2MP3, there is actually important stuff. But yeah. Yeah. Was I part of the first mechatronics graduating class? The second, actually. Yeah, the second ever graduating class. A lot of people in the first year. A lot of people in the should have been in the 2009 graduating class and graduated during my. Anyway, I digress. So we need to know, how does an embedded system interface with external components and external inputs and outputs? What kinds of buses and bus protocols are used? How do sensors and actuators work? What are the design tools available, and how do they assist in designing? Mechatronics 3TA4, or 2TA4 in this case, introduces you to these topics and the design of simple embedded systems. The labs will provide hands-on experience. Frankly, this was my favorite course from my undergrad. I'm actually thrilled to be teaching it. 3TB uses hardware design languages. and tools to design more complex embedded systems. Mechatronics 4AA4 discusses how to implement several systems using one processor, real-time operating systems, and introduces real-time issues, priority-based scheduling, resource sharing, etc. Lots and lots of sort of nuts and bolts of computation stuff in 4AA4. And that's it. So that's topic 0. So let's move right along then, shall we? Unless are there any questions about that before we move on to this slide, which has a weird aspect ratio? You thought I was under 30. Yeah, I look it, right? But I'm actually, like, born in 88, so 33 turning 34 next month. I'm younger than I look, right? Pelanovsky. Rings a bell, but I couldn't tell you for sure. I know he was pretty young at the time. Yeah, Aaron is, I really like Aaron. He's, on top of things, you know? Actually, I was kind of snooping through the top performing students from last semester, 3TA4 last semester, to see if I could poach any of them to be TAs. Because, you know, I find that's not a terrible recruitment strategy for TAs sometimes. I don't use it, like, all the time, but, you know, sometimes. And I noticed that Aaron was actually the actual top performing student in 3TA4 last semester, so should do pretty well as a TA for this class. So, so let's talk chapter 1. Where's the textbook? There it is. So, for those of you who may be following along in the textbook, we're talking right now about chapter 1, See a Program Running. Yeah. Yeah, Aaron is back. He's I forget which section he's on, but it's in the syllabus. It's in the syllabus, whichever section he's on. He's only got one section, so I've also asked him to take a look at Piazza, like shared Piazza duties with Fernando, who also only has one lab section. And we managed to find the 4th TA, although I don't think I've updated the syllabus with his information yet. But anyway, so chapter 1, we're going to be talking about, roughly speaking, like, overall, this is what the architecture of a controller looks like, all right? But first, let's motivate this. So we're going to go through a series of devices that are all ARM architecture, right? So embedded systems in general, lots and lots of things are embedded systems. This slide sort of focuses on the more high-tech kind of stuff, but there's like a large number of low-tech kind of applications that also involve embedded systems, as we've already covered. So this is what an Amazon warehouse looks like, if you're not sure. And you see these little orange guys underneath these shelving units? Those are the robots. The robots that run Amazon warehouses, which is kind of fun. These guys would also be embedded systems, very technically speaking. So we're going to talk a lot about assembly programming in this class, despite the fact that it's not really being required very much for the labs. Like, you're going to be expected to have like a knowledge-based understanding of these types of like really low-level programming concepts that interact very highly with assembly. So, you know, you will note that the title of the textbook is Embedded Systems with ARM Cortex-M Microcontrollers in Assembly Language and C. Note that assembly language in the actual textbook for this course gets top billing. The best part about the Amazon robots is that they can't unionize. Wah, wah. Totally agree, though. Man, like, the amount of money that I've given the union over the years for basically nothing. Jeff found workers that don't need to go to the bathroom. Yep. Yeah, absolutely. So, embedded systems, right? It's like, when you guys took 2MP3 with me and we talked about assembly programming, one of the things that I motivated assembly programming with was this idea that you could optimize things more highly in assembly than you ever could just writing a higher level language. And I said stuff like, no matter how good your compiler is, a human being going after assembly, like doing assembly level optimization, is always going to outperform it. So, first of all, in embedded systems, performance is everything. Cost is everything. Embedded systems are designed for very large product runs. So, as I said last time, the lower you can ratchet that cost down, and even very small amounts of decreasing in, like, even if you're able to decrease the cost by a very small amount, say a couple of cents, you're probably going to pay your salary for whatever product, right? But yeah, and so we're trying to reduce the production cost at the expense of engineering cost, and that's often like what you want to do. The larger the product run is, the more you want to do that. Were Game Boy games programmed in some assembly style language? I think so. Lord knows they were probably optimized at that level. One of the big advantages of assembly programming is you can write programs that are physically much smaller than the programs that you would write in a higher level language, because everything gets compiled down to machine code anyway, right? Assembly language is one-to-one with machine code, but as we're going to see, a couple of C statements explode to a whole bunch of machine code, right? So, essentially, way back in the day when you were programming a Game Boy cartridge, a lot of those things only had like 16 kilobytes of memory if you were lucky. So, you imagine, like, okay, let's see. I'm going to look it up right now. Cartridge size Pokemon Red. So Pokemon Red is kind of like Red and Blue. Like, one of the interesting things. No, sorry. Program size Pokemon Red, maybe. Yeah. Okay. So I tell a lie. Some of the earlier Game Boy games probably were on the order of 16 kilobytes. Pokemon Red is 47 kilobytes. Right? So imagine writing a and that's all program, right? So writing an assembly, you can perform the same work as a C program that would be, twice to 3 times that size. But yeah. Robots don't need to evacuate in case of robot uprising. So, assembly isn't just another language. Again, assembly is one-to-one with the actual instructions as executed on the processor itself. So learning how assembly language works teaches you how the processor itself works, right? Assembly programs run faster than higher-level languages, and that is, when you get down to this level, that's actually because the program size is a lot smaller, right? Each individual command takes time to execute. So if you have fewer commands, you take less time to execute. Using profiling tools to find performance bottlenecks and rewrite that section of code in assembly is often a useful thing to do. Like, at least this last semester, towards the end of 2MP3, I talked about profiling a little bit. So if you have latency-sensitive applications such as air traffic controlling, that's something like if you need fast output, assembly is fast. And standard C compilers do not use some operations that are available on ARM processors, such as rotate right and rotate right extended. So one of the things about a C compiler, like take GCC for instance, GCC, generally speaking, is designed for Intel chips, right? So because it was developed on Intel chips. So it's not unreasonable to expect that the sort of base of commands that GCC would compile C into would be that subset which is shared between Intel and ARM, right? Which means ARM has commands which might be useful, but a C compiler wouldn't use because it's not been programmed to use it, because it's supposed to be more cross-platform than that, right? So the types of places that you will find assembly code are often in boot code, because that should be fast. Device drivers, because it's often just easier. Compilers, assemblers, and linkers, because these are, shall we say, compilers can take a really long time, so it makes sense to optimize them. And a test and set atomic assembly instruction can also be used to implement locks and semaphores, which are things that you won't know about until you're in fourth year. Cost-sensitive applications can, it depends, right? Again, it depends on how big the product run is. With large product runs, you increase the non-recurring engineering cost in order to lower the production cost so that you make more money over time, right? You are better able to understand high-level languages when you know what they're being translated into. So, why ARM processors then? Why ARM? Why not like RISC-V or RISC-V or any of the any of the competing processors? Like why ARM specifically? First of all, it stands for Acron RISC Machine, and the answer is because it's like hugely dominant in the market. So in 2010, they manufactured 6.1 billion ARM-based processors. And as of 2019, 150 million ARM processors have been produced. Now, obviously, not all of those are going to be actively running, but 95% of smartphones use these things. You see them popping up all over the place. They're even beginning to get into like computers proper. What is a mobile computer? I'm assuming that's like a laptop. Like Chromebook. I'm gonna say Chromebooks. That's probably Chromebooks. Or things in the Chromebook category. So that's a lot, right? 95% of smartphones, and like smartphones have completely revolutionized what it means to be a human being. So ARM is the technology that's enabled that. Because it's power efficient, my friends. So, So this is the guts of an iPhone 7, right? You'll notice that the big chip in the middle has 6 ARM cores in it. ARM version 8, in fact. Computers with legs. Yeah. What's the meaning of Acron RISC machine? Oh, that's just the name of the processor, but it's normally called ARM. As one of your colleagues pointed out, ARM is an acronym. This is what it stands for. There's an acronym within this acronym. RISC stands for Reduced Instruction Set Computer. Or, so it's, full title is Acron Reduced Instruction Set Computing Machine, something like that. The C and the M are kind of redundant, but wasn't the Surface Pro X ARM based? Probably. I know one of the one of the things that's kind of controversial about ARM processors in general is that they lock you out of the bootloader, so you can't really install a new operating system on them very easily. So that, that ticks off the Linux nerds, basically. So, Amazon Echo, which is the same board as Alexa, or that's the board on which Alexa lives. It has a Texas Instruments digital media processor, which in its core has an ARM Cortex-A8. The Kindle HD Fire has a OMAP dual core processor, so possibly not ARM then. The Fitbit Cortex M3 ARM processor. The Galaxy Gear, an M4 ARM Cortex M4 MCU, which stands for microcontroller unit or microcomputing unit. You sometimes see MCU for as the acronym instead of CPU, but it's a CPU. Pebble smartwatch uses an ARM Cortex M3. So you can see we're kind of going down in terms of power with these things, except for this one. Oculus VR has a ARM Cortex M0. The HTC Vive has a ARM Cortex M0. So it's like Oculus, Vive, both use the same processor, folks. Do all ARM boards come from the same manufacturers? That I couldn't actually tell you. So what I suspect happens is the ISA, the design specifications for ARM processors, will be owned by an electronics company, but likely the manufacturer of those chips is sold out at contract, right? So they're probably a bunch of different manufacturers of the chips, but the intellectual property of the processor itself is held by ARM. I would suspect that would be how it would work from a business perspective. So, the Nest learning... I know I'm kind of beating a dead horse at this point, but this thing's also got an ARM, the Nest thermostat also has an ARM core. Samsung Gear Fit fitness tracker, also an ARM Cortex M4 CPU, etc., etc. So you can see, it's used everywhere. Everywhere. Right? So... So I guess what I'm trying to say is this class is relevant. So let's talk about how CPUs let's talk about the architecture of a CPU for a moment. So I'm gonna skip a couple of slides down and then I'll come back up again. So, generally speaking, and you'll probably have heard me talk about this in 2MP3, the model of computation, which is used like in general, is the von Neumann architecture. So in von Neumann architecture, you have a central processor, which does the processing, and you have a memory unit, which is external storage, where the data is stored, right? And there's a communication protocol, like a communication bus, between the processor and the memory unit. This is how laptops work. This is the basic model of computation that all processors use, right? It's like you have input coming in. You have input coming in, right? You have the CPU, which interacts with memory, and you have the output coming out. This is your top-down view of how things work. Oh, yeah. Yeah, if anybody knows an answer to a question that I've been asked, please feel free to step in if you know more specific stuff, right? Like that's actually one of the things I'm going to miss about doing lecturing online, is that, people are just kind of free to contribute to the discussion. And that's harder in person, because there's like more of a activation energy of people having to get over the social anxiety of putting their hand up in class, right? But anyway, so this is good, and like von Neumann architecture served us extremely well for a very long time, right? However, some clever folks at Harvard came up with a refinement of von Neumann architecture, which improves performance and speed and all of the rest of those nice, tasty metrics that have enabled the modern age. So, Harvard architecture is very similar to von Neumann architecture. The essential difference is that rather than including the instruction and data memory in the same memory unit, the instruction memory and the data memory are separated. So they are accessed via separate buses, right? In person, we have to deal with social interaction. Smelly humans. Yeah. Yeah, when you're in a room with other humans, you have to smell them. Man. So I'd actually like to put this question out to the crowd. I'd like to start a bit of a discussion about this. What do you think the advantages are, like the specific advantages are, of Harvard architecture over von Neumann? Does anybody have any ideas about that? Like, what would this make better? I know the answer. I want to see what you have to say. What's the difference between the two memories? So one of these only holds the instructions, like, of the program itself. The other memory cell holds the data being used by that program. So, let's say you have a C program, right? You compile it to the code, and while that code is executing, the data that, like, the place the variables are being stored, essentially, is in the data memory, which is distinct from the instruction memory. Would it be faster? It is faster, yes, but why? If one is having an issue, it doesn't affect the other. Yeah, sure, but if you can no longer access the instructions of the, if either of these goes down, that's critical failure, right? It's like, if you can't get at the program, you can't run it, and if the program can't store and retrieve memory, then it's done, right? If something breaks, would Harvard be easier to fix since they're separate? Well, the thing you have to understand is that these things are, generally speaking, embedded in one chip, right? So the replaceable part is the entire controller, not either the instruction memory or the data. Well, now that I think about it, that's probably not the case. I'll pull that back one level. if something breaks on your Fitbit, you throw out the entire Fitbit, right? You don't replace chips on the board anymore. Like, it's like, you can do surface mount soldering, but it's like the types of embedded systems we're talking about right here are practically impossible to repair, right? Processor can access both at the same time. Thank you, Ethan. That's a major one. So because these two memory buses are separated, they can be run simultaneously. So you can be loading instructions at the same time as loading variables. This improves, like, because like when you're running a program, you're loading as many, like you're often loading more instructions than memory, right? So like being able to do both in parallel, significant speed improvement. Is it sort of like how functions, how separating them allows it to be more efficient when being used many times in different contexts? A little bit. Oh, wait. Oh, yeah, sorry. Rayhan says the same thing. Yeah, sorry. Sorry. Yeah, both of you said the same thing at the same time, but I saw Ethan first. Sorry. And Omar says, less fighting over bus bandwidth, less bottlenecks. Yes, because they're different buses, right? So they aren't sharing bandwidth. Yeah, a few of you came up with that one. So yeah, it would cost... So whether or not it costs more is kind of like... Like, once it starts getting down... like we're not really talking about optimizing the costs of individual chips. That's more 3TB4. We're interested in optimizing the costs of like processors and their peripherals. It does impact the stack, Avery. You're right about that. But CPUs don't have serial processing, so why would it matter? Good question. So, basically class is over, but I'll give you a brief taster, right? So, inside of the so when you fetch an instruction, you have to like decode that instruction before you execute it, right? So, and you can pipeline these operations, right? Do we have a slide on pipelining? Yeah, so you can basically you can set up sequential instructions to be operated on, right? And the so the ability to fetch the memory separately from the instructions means that, you know, when you decode, you can also fetch, but at this you're not occupying that clock cycle with fetching the next instruction. So you can load the next instruction while you're fetching data from the previous instruction. Pipelining is going to be a very important concept, which we're going to talk about in more depth later on. But it does work. It does work. There's a reason that Harvard is an improvement and that ARM cores use it. Why would you need multiple cores for... You would need multiple cores for Harvard style, no? Curious why number of cores matters. So... No. Right now we're only talking about one core. So if by core you mean combination of control unit, arithmetic logic unit, and registers, we're still talking about one core here. But yeah, it's like the instructions are getting loaded straight into the control unit, and the data memory is being like interacting directly with the registers. These are separate parts of the chip, right? So you can't actually load them in parallel. That's one of the like big conceptual gaps that you're, or that's one of the great conceptual leaps forward that you're going to make over the course of this course and embedded systems too, is there are, in electronics, processes that can be executed in parallel, right? That's the great advantage of electronics over doing everything exclusively in software. electronics are capable of true parallelism. That is, two circuits can be doing different things at the same time, right? It just increases your power consumption. In software, you can always only do one thing at a time, right? So, at any rate. So, are ARM cores better than the ones we are currently using in PCs? Well, I will ask you, is your laptop better than your smartphone? It's like, for many applications, ARM is better than Intel. For other applications, like the big chips are better than ARM. It really depends on the application you're going for. Yeah, better for some applications and not better for others. They're kind of creeping up though. This has been the trend over like the last 20 years or so, is that like ARM chips are getting better and better and faster. Intel chips are like, I say Intel, but I'm also talking about AMD. I'm talking about like the old traditional chips, right? The older traditional chips are constrained by their ISAs, right? Once you add an instruction to a chip, you can't take it off because that would make old programs not run on new chips, which is not something you want, right? So over time, the set of instructions on the sort of the old guard chips gets bloated, right? Which means that, they get bigger and bigger and require more and more power, which means they're not suitable for these sort of lightweight, low power applications. Whereas ARM, right? Reduced instruction set computer. Small number of instructions, and the design effort is to try to not add a bunch, right? So that means they're better for low power applications. Does ARM only work on smaller scale then? I mean, you could totally build a laptop with an ARM processor. Like, there's nothing preventing you from doing it, right? It's just, their operating system, imagining, you would have to recompile everything for it, right? There's a reason that, Android runs on ARM, and you wouldn't think about, taking a laptop and installing Android on it, right? Aren't quantum computers supposed to function in parallel too? Yes, but that's, due to quantum superposition principles. The reason you get parallelism in electronics is because you can literally have two wires running in parallel, right? Or two circuits on the same board. Whereas the parallelism in quantum computing comes from the individual components of the quantum computer being able to occupy more than one state at once because of quantum superposition. It's only a matter of time before phones can run Crisis. Well, the one thing that they haven't got is GPUs, right? So, we'll see, though. But yeah, anyway, so that's class. Thank you very much for your time and attention today, folks. And we will resume next week. Take her easy.